There's one last issue involving conic sections that we have yet to tie up, and that is, why is it that conic sections are produced in these two totally different ways? So when we first started talking about conic sections, I described them in terms of taking cross sections through a cone like this. Right here I have a picture of this cone. It's being sliced at an angle by a plane, and it gives us this sort of elongated circle shape, which we've been calling an ellipse. But when we actually got down to the nuts and bolts of an ellipse, we described it with more of a like plane geometry, like two-dimensional geometry kind of description, where we chose two foci and all of the points so that the sum of the distances to the foci was a constant. That is the shape that we called an ellipse. And it's not at all clear that these two shapes are the same kind of shape. I mean, they're both vaguely oval shapes, but that doesn't mean they're both exactly the same kind of shape, right? So why do these two descriptions actually produce the same shapes? It's a surprisingly tricky thing. I think that the ancient Greeks knew that these two shapes were the same, but the way that they explained it is actually kind of involved and not intuitive. But centuries later, in fact millennia later, I think this happened in the 18th or 19th century, someone discovered a pretty straightforward way to demonstrate that these two shapes are actually the same kind of shape. So both of these descriptions do generate the same oval shapes. So these really are the same ellipses. To get things started, there's one kind of setup fact that we need, which is this. If you have a sphere, okay, so here's a sphere, and a point not on the sphere, so out here, and you look at all of the line segments tangent to the sphere, so like this line segment, this line segment, this line segment, so these are all tangent to the sphere. Here's another one. It turns out, so this isn't, this, it turns out all of these form a circle around the sphere. That's not the important part. But the important part is that all of these are the same distance from the point not on the sphere. Okay, so all of the, from a point not on the sphere, all tangents to the sphere are the same distance from the point. Right? That's kind of intuitively plausible. To prove it, I think the way to prove it is to draw a line segment from this point to the center of the sphere, and then imagine rotating this diagram around that line. Well, if you rotate the diagram around that line, all of these tangent line segments will just rotate into other tangent line segments, and that means they all have to be the same length, right? If you can rotate one into the other, they must have been the same length, because rotation doesn't change the length of anything. So that is one important fact that we're going to use, right? So call that the party hat theorem, since this looks like a party hat sitting on top of someone's head. So all of the tangent lines to a sphere, all of the tangent line segments to a sphere from a given point are all the same length. Okay, so here's how we can show that when you slice a cone, you get the same thing as when you choose foci. Right? The tricky part about this, so here's that cone diagram. The tricky part about this is figuring out, well, where are the foci going to be? Right? Because we have this oval shape. To verify that this oval shape that we've made by slicing this cone, to verify that it really is an ellipse in the two-dimensional geometry sense, we have to identify where its focuses are. You might think, well, maybe the vertical line through this ellipse is located on a focus, but actually doesn't really seem like it. It's not going through the center, but it's too close to the center to be an ellipse, so maybe not. The trick that someone came up with 2,000 years after the ancient Greeks figured out a lot of this geometry is the trick they came up with was imagining sitting a sphere into this cone, right? Now a sphere, any size sphere, will fit into this cone. The bigger the sphere is, the higher it will sit in this cone. If the sphere is very small, it will settle down a long ways into this cone, right? But any sphere can be put into this cone so that it's just touching the cone. Well, if we can continuously make a sphere grow larger, it will sit further and further up in this cone. But that means that there are two special spheres that we can put into this cone, right? There is the sphere that is just large enough that it touches the plane from below, like this. And then there's the sphere that is just small enough that it touches the plane from above, like this. So both of these spheres are tangent to the cone around these circles that I've marked. And they are also tangent to this plane, our slicing plane, at one single point. Okay. In fact, those points are probably important, so let's mark those points. It's those 2 points. Well, now that I have those 2 points marked on this slicing plane, now you probably have the idea. These two look like maybe those are the foci of the ellipse. So that's our idea. Maybe it's these 2 points that are the foci of the ellipse. Well, now we need to prove that any point from the ellipse to these two points add up to the same length, right? Because that's the plane, the two-dimensional plane definition of an ellipse. So here's a point on the ellipse, and we can move it around, right? And I've marked the line segments from this point to each of these. I'm going to call them focuses, even though we don't know that they're the foci yet, because they are the foci, but we don't know that yet. So I've marked those 2 lengths, and right. So we need to prove that. So I have a green dotted length and a yellow dotted length, right? And those lengths are different when I move them around the ellipse. And we need to prove that the sum of those 2 lengths is always the same, no matter where we are on the ellipse. And that actually looks like maybe it's not true. Like this length, if you add those 2 together, that looks like it's a much longer length than the sum of these 2 lengths. But there are some perspective effects, right, that are going on. These 2 look short, not because they are short, but because we're looking at them from a very oblique angle, right? If we look at them from out here, maybe it looks a little more plausible that the sum of the lengths is the same. So, I mean, what I'm trying to say here is that it's hard to tell if the sum of the green and the yellow is staying the same just by eyeballing it. So that's really why we need to prove that the sum is always the same. It's because we can't tell. Okay, so how to prove it? Well, the idea is this, right? What we haven't really made use of yet is the cone, right? There's this whole cone that this situation is sitting inside of. And one way to make use of the cone is to, right, that we have one important point on the cone. It's the point that's on the ellipse out here. But there's another important point on the cone. It's the point of the cone. So maybe we should join those 2 lines together like this, right? And that gives us 2 other lengths that kind of seem important. There's the length from the point on the ellipse down to this bottom circle down here. And then there's the point on the ellipse to this upper circle up here. So let's mark those like this. Like this. There we go. So that gives us a solid green and a solid yellow. All right. Now, the surprising thing about this is where we're going to use that party hat theorem. The surprising thing about this is that the dotted green length is equal to the solid green length. And the dotted yellow length is equal to the solid yellow length. So let me explain that for the greens. Now, this dotted green length, that is going from the point on the ellipse to this tangent point on the sphere, right? It's going to this point on the sphere because that's how we define that length. The line segment from this point up here is going to this point down on the tangent circle for the lower sphere, right? So it's going along the cone, but the lower sphere is tangent to the cone. So this solid green length is tangent to that lower sphere as well. So these two green lengths, the solid and the dotted green lengths, are both tangent to this lower sphere. But now the party hat theorem tells us that that means those two lengths are the same. Right? We have two line segments tangent to a sphere coming from a single point. So they have to be the same length. So the dotted green length is equal to the solid green length. Well, the yellows are the same length for exactly the same reason, but with the upper sphere. The dotted yellow length is coming from the point on the ellipse and is tangent to the sphere over here, and the solid yellow length is coming from this point on the ellipse, and it's tangent to the upper sphere at this tangent circle, again because this sphere is tangent to the cone at that circle, and the yellow length is in the cone because it's joining 2 points in the cone. So that means the yellow lengths are the same. So the dotted green is equal to solid green, and dotted yellow is equal to solid yellow. Now remember, what we are trying to prove to ourselves is that the sum of the dotted lengths are equal. Well, the dotted lengths are equal to the solid lengths, so we can instead ask about the sum of the solid lengths. But as we move this point around the ellipse, right, the sum of the solid lengths, like they stay lined up along the cone, and the distance that they make is the distance from the bottom tangent circle to the top tangent circle. But like those tangent circles, the distance between the tangent circles is always the same no matter how you measure it along the cone, right? You can kind of see the only thing that is changing for this, the sum of the solid lengths, is how the point on the ellipse splits the sum of the lengths into two different lengths. That's the only thing that changes. The total length is always along the cone from the bottom tangent circle to the top tangent circle. So the sum of the solid lengths is always the same. That means the sum of the dotted lengths is always the same. And that means that we have correctly identified the two foci of an ellipse. So finally, we see that the 3D version, or the 3D definition of an ellipse, gives us the same shape as the 2D definition of an ellipse. So this is all just for ellipses. There is a similar argument that works for slicing hyperbolas and for slicing parabolas. I encourage you to work one of those out if you're curious, because it's a nice little exercise in three-dimensional geometry. For both of those cases, the trick is finding the right way to nestle a sphere into a cone. So I'll leave the details for you.